Yeah, thanks a lot for Sanchit inviting me, and yeah, excited to give this talk. So yeah, let me start. So today I'll be mostly talking about a bit of three of my works in general, where I'll be focusing on how do we accelerate multilingual RAG systems, focusing on retrieval, relevance, and generation evaluation. So to start with a bit about me, so I did my undergraduate from BITS Pilani, Goa, and then for a few time after my graduation, I was a software engineer at Nolscape. I think so back in 2021, 2019, sorry, I kind of switched as a NLP research assistant at UKP Lab. And since then, I'm currently doing my PhD at University of Waterloo, just started my fourth year here, and also did two internships previously, one at Google Research and more recently at Databricks. So yeah, you can find me on Twitter at this handle. So it's Beer Mug, and my email is also mentioned here. So let's start the talk with, in general, talking about native speakers across the world. So according to the survey, there have been about 7.2 billion people on Earth. And for this survey, at least 6.3 billion people were included, out of which 4.1 billion people have kind of speak one of the 23 most spoken languages as a native tongue. So if you see this chart on the right where I have enlarged it, you can find that different languages are mentioned and the native speaker count is mentioned in millions. So these contain many of these Indic languages. You can find Hindi, Telugu, sort of Tamil, Bengali, Marathi as well. Moving on, let's look at English. So if you see English, English is a small icon here, which I've shaded. So if you focus on English, actually only the 4.6% of the speakers worldwide are have their first language as English. So there are only 4.6 L1 speakers currently. And the moment you include L1 plus L2 speakers, you only come up with 18.1%. So what I really wanted to show is that still there is a lot of huge amount of speakers kind of which are present around the world and who do not speak English. Yeah, I'm getting some feedback from the conference room, I feel like. So reduce the volume. Yeah, 1 second. Yeah, no worries. Yeah, better? That's possible. Yes, yeah, that's great. Awesome. Yeah, sorry about that, but yeah. So this kind of like what the motivation was to kind of show that, we like not just all research should be kind of focused on English, but we should also focus on different languages, which caters to more speakers across the world. One of the motivations of why I wanted to work on multilingual RAG, and personally, I find these kind of options or choices to be important. The first is more inclusive and to provide better resources. So what I want to do is kind of provide resources to the community, which would hopefully encourage them to drive more research in this particular direction. More empowerment and participation. What I really like is that if you do something more local, people within our family or in our extended family, they can actually appreciate more, use these systems also in their native language. So this kind of empowers them and also helps them participate in these applications. And third is I want to target a much more wider audience. So once you do multilingual RAG, you can access documents from multiple different languages. So ideally, you have a much more richer source of information, and you can also target a much more wider audience. So yeah, today I'll be kind of keep on coming back to this diagram, which I've called it kind of a Swifties diagram, where I basically it shows how a typical naive multilingual RAG pipeline is constructed. So the question is something like, how Taylor Swift's age affects a relationship, and this a user will provide. And you then first would give it to a retriever model, which has certain human-generated documents in a corpus. For example, in our case, we are using Wikipedia in a certain language. And you retrieve top K documents then given the question. Once you have retrieved your sort of top K documents for a given question, you use it along with the question, use a prompt, and provide it to the generator model. And after the generator model gets the question and the retrieval documents, you basically have the RAG answer generation stage, which the generator model answers using context present in the top K docs and using the question as well. So the first part where I mentioned, so I'll be talking about retrieval. So this comes in this area, which talks about multilingual retrieval and how we can evaluate different retrieval systems on that. The second part where I'll be talking about is relevance assessment, where given a question and given a list of top K retrieved documents, we are kind of evaluating, does the generator model really understand that these top K documents as a subset will be able to answer the question or not? And the third part will focus on the generation part. So in this case, I would be evaluating, given the generator model and the answers, how well are the answers formed? Do they cite appropriately? And whether they are fluent or not. A little bit on why I kind of wanted to work on these projects. So this is kind of a text snippet of a really nice blog post, which Omar Khattab kind of mentioned on September 4th. So I definitely do recommend you can kind of read this blog post. What I really wanted to focus is on point one here, where Omar mentions that, ideally, you should invest in projects, not papers. And this is kind of like have been my motivation in all the multilingual RAG work, which I'll be presenting today. Informally, I would have named this talk to be something like a multilingual RAG universe, where I kind of find all the three parts crucial in basically for multilingual RAG. And yeah, all three together kind of forms like the team which is required to kind of accelerate RAG across different languages. So moving on now to the first part, where I'll be talking about MIRACL, which is basically a multilingual retrieval dataset covering 18 different diverse languages. So this was a work done by Christina Xinyu Shang and myself. And some of these slides have been modified from Christina's. So like I mentioned, so in part one, we wanted to focus on retrieval evaluation in RAG. So just to remind you from our diagram, so this is the part where you have the question, you do a retrieval, and then you have your top K retrieved documents, which are then evaluated using a metric. So the objective for this is that overall, we want to see whether a RAG system can retrieve the most relevant source documents or not. The setting which we follow in our work is monolingual. So this means that both the queries and the documents are in the same language. For example, it can be Hindi or some other language. And the input for retriever part is you would get a user question, which is provided as input, and you need to output a ranked list of passages as the output. So let's look at some overview and some statistics from the MIRACL dataset. So it provides you high quality training and evaluation data for monolingual passage retrieval. It was actually constructed using a large scale human annotation. So we had to spend about like 5 to 6 months on actually getting all the annotators, getting all their work, like kind of managing them. So it took us about 5 to 6 months actually to construct the whole data set. So it has about 10K hours of work from 31 different annotators who are native speakers of different languages. It contains 18 different languages. So what I plot here is that plot the speaker count and the Wikipedia size, which we find across different language families. So if you see, English is the only one which is on top, where you have a huge amount of Wikipedia information available within itself. But more or less, for other language families, you can find that there is kind of a linear increase where the more amount of speakers means that you have more amount of information present in Wikipedia. Lastly, just to compare with some other data sets, MIRACL contained like 726,000 human annotations, relevance judgments across all languages. So this is really much higher than all the other data sets which are present, which were present back in 2022 during this introduction of the work. So how MIRACL was constructed was we kind of went through the literature itself and tried to follow what was already done previously in literature. So our construction was very similar to how tie-dye QA was constructed in two phases. So the first phase involved query generation, and the second one was relevance assessment. So in phase one, query generation in very layman, simple words was that you would have a Wikipedia dump in a particular language. So you would scrape it, you would get the Wikipedia dump, and then you would convert that into a passage collection. And using that, what we formed are some small snippets of 100 words, which basically contained the initial information about a Wikipedia article, which was provided to these native speakers and actually then used to generate certain queries about it. So this was phase one, where given some queries, you generated questions using these prompts. And one important thing to note is that we wanted the annotators to generate queries which cannot be answered by these prompts itself. So we wanted to generate some related queries, but not exactly answerable by the prompt itself. In phase two, we moved on to actually taking these queries, do a hybrid retrieval stage where we incorporated multiple different models such as BM25, MDPR, and MColbert. We retrieve candidate passages, top 10 candidate passages, and then use that, provide that to our native speakers, which provide us back the relevance judgments of a query passage pair, whether it's relevant or not relevant. So this is the phase two of the MIRACL construction. MIRACL was kind of introduced back in 2022, and we had like a task, a competition around it in Wisdom 2023 or 2022, and there was a lot of participation amongst many teams as well. And ever since, we also find that MIRACL is currently now being well adopted within the community. So many multilingual retrieval models, such as like Gecko, Embed V3, the multilingual E5 models, have been using MIRACL as both as either the training data set part of it or the evaluation part of it. So I compiled a few state-of-the-art models currently, which I found their numbers on their papers, and I compiled them. So you can see there are like different models here, such as like, the Embed multilingual V3 model, which is by Cohere, the BM25 Contriver, MXTR, and similarly the E5 models, and also lastly the BGE. So this is like a huge table, basically 16 different languages, all plotting NDCG at 10. Just to give you a TLDR on what we find currently in MIRACL is that BGE M3 is the model which currently achieves the best performance on MIRACL in terms of NDCG at 10. Overall, we find that hybrid search works well for multilingual retrievals. So we also find that BGE M3 actually involved both dense, sparse, and lexical representations. So we kind of see that in this direction of hybrid search is what is best for multilingual retrieval. And unlike what is being seen in English, I still find that commercial APIs are currently not significantly better than the open source alternatives, which are there at least on MIRACL. So moving on now, so we talked about retrieval. Now let's kind of dig into the second part where I'll be talking about the relevance assessment. So in this case, I'll be talking about our work, which is knowing when you don't know, a multilingual relevance assessment dataset for robust RAG. So this was recently accepted at EMNLB 2024 in the findings track. So in this part two, remember in part one, we talked about retrieval. So in part two, we would talk about relevance assessment. In this case, how we do the assessment is that our objective is given a set of top K retrieved documents and a question, we actually want to evaluate whether the LLM can help identify relevance in the retrieve context or not. In our case, we considered Oracle documents. So we actually did consider them or the top 10 passages which got annotated and used those for our paper. And lastly, how we labeled the task was more of a binary classification task. In a way, we kind of say whether, or we evaluate whether an LLM can identify the relevant passages or not. So NoMIRACL more or less talks about the multilinguality in context understanding. So our motivation is that, often there are retrieval errors in RAG scenarios, and it can provide you with bad search results. So bad search results means that all of the passages are non-relevant. So in these cases, ideally in a real world scenario, you would either want the generator to output saying something like, I do not know the answer for the query, or you would want it to retrieve again. But ideally, you should be able to capture these kind of cases. And so if you see the example on the left, this is one of the examples. Like, for example, the query asked by a user was, what does the AC button on the calculator stand for? And the top documents, the first one talks about actually power electronics, which talks about the AC voltage controller. And the second one actually gives you the calculator, but it doesn't talk about the AC button itself. So in this case, you actually found that, a majority of these documents are really not relevant, or they cannot be used to answer the question of what does the AC button in the calculator stand for really. So our research question for the paper was more like, do LLMs understand these relevance across languages? Like, does it really understand whether your top K passages contains relevant information to answer the question or not? And in order to do this, we do an evaluation in a binary classification objective where we kind of constructed two subsets, the non-relevant subset and the relevant subset. So the non-relevant subset more or less contains all the passages to be non-relevant, whereas the relevant subset would contain at least one passage which is relevant to the input question. Like I mentioned, so we formed an experimental setup where we construct the relevance evaluation objective as a binary decision tree in a way. So you have yes, answer is present, in wrong, because in the non-relevant subset, you really want the model to output, I don't know. Whereas in the relevant subset, you want it to output, yes, the answer is present. And if the model says, I don't know, that's incorrect. So in the non-relevant subset, you expect the LLM to refrain from answering. In the relevant subset, you would ideally want the LLM to recognize the relevant passage and provide a valid answer to it. In order to measure this, we introduced two metrics. One is the hallucination rate, which I kind of classify, or which I label as errors on the non-relevant subset. So in this case, if a model says an answer is present in the non-relevant subset, this considers to be a hallucination. On the other hand, what I consider to be an error is when a model says, I don't know on the relevant subset, meaning that it's not able to figure out the relevant passages within the context.
I have a question, Nandan.
Yeah.
So everything here is monolingual, right? If the question is in English, the relevant documents you'll be evaluating for English, right?
That's correct, yes. Yes, our setup is monolingual. I think so. I'll talk about that in the end. I think so. We started with MIRACL, and then in general, we had data sets which were present in monolingual form. So I kind of extended that. But ideally, I feel like in future, we can also extend this to like cross-lingual and monolingual scenarios. Okay. Moving on. So how we actually constructed NoMIRACL was actually it happened during MIRACL construction itself. So how? So remind you, like in phase 1 of MIRACL, actually we would want human annotators to construct queries using the whole small 100-word text for inspiration. What we found was like a majority of these generated queries, and once we did retrieval for it, they all came out to be non-relevant. And there were 2, 3 reasons for this. One, we found the majority reason is that often the query, the information which it asks, it's probably out of scope in Wikipedia. Or second, it may contain some spelling mistakes in the query, which is leading to like incorrect retrieval. So these queries and passages were kind of wasted in MIRACL, because in MIRACL for a retrieval subset, you actually need relevant passages given a query, but they were utilized in our case to form the non-relevant subset in NoMIRACL. So we were able to efficiently utilize and not waste this all this effort which went into annotating these query and the passage labels. So just to remind you, so the annotation phase was exactly similar as the MIRACL one. So you had the phase 1 where you would the annotator would generate a query, then it would go through a retrieval system and you would retrieve some top-K retrieve passages. The only difference is right now, whenever we have all the passages which were labeled as non-relevant, we found that to be the non-relevant subset in NoMIRACL. And correspondingly, the relevant subset of NoMIRACL is the MIRACL dataset itself. So these are some stats. If you're interested, you can look into the paper. But overall, we had a huge amount, like we have almost about 40 to 50K in total pairs for evaluation. So we evaluated 14 different LLMs across 5 different families. So this included both closed and open source models, like GPT 3.5, GPT-4, GPT-4o, Mistral 7B, Mistral 8 cross 7B, and the Orca models, Aya model, and the Llama model.
I have another question. So, sorry.
Yeah.
So, like for the Orca, I'm interested. Like, why did you choose Orca? Because like the models are trained on a synthetic data. Like the whole setup for the Orca models is train a model using the synthetic data generated. So, like, the data itself might have certain problems. So, like, would the results from those models actually translate to the RAG pattern? Because the rest of the models are like have a mix of both synthetic data as well as data from the web. But Orca is an interesting choice. Any reason why did you choose that model?
Yeah, instead of 5.3, I think.
Yeah. Anyway, like,
Yeah, I think so. So one reason was I'm not sure when exactly 5.3 came out, but the NoMIRACL paper was like back in 2023 early, 2020, 2023 summer sometime. So I feel like the 5.3 models were not available at that point of time. So that's why we initially at that point of time, Orca was present, and that's the one we chose. For the specific reason for why we chose Orca, I currently don't remember. I feel like we were evaluating at that stage, like we wanted to evaluate different models, and we found like, Orca was kind of being like, I think so at that point of time, Orca was heavily in the news as well. So I just wanted to try it out. Yeah. But yeah, right now, I think so when I'll move on to the third part of the talk, I do have 5.3 and their results for the generation part on that case. Okay, yeah, so this is basically a high-level summary of the results in NoMIRACL. So here you can see on the x-axis, I plot the accuracy on the non-relevant subset. So the more towards 100%, the better. And on the y-axis, I plot the accuracy on the relevant subset. So if you actually follow the flag, this is ideally you would want your models to perform on this end of the graph. So you would want them to perform well on both the non-relevant and the relevant subsets. So what we found was, in general, a lot of existing like Llama 2, Orca 2, and Aya models were like, they would do well on the relevant subset. However, on the non-relevant subset, they achieved over 80% hallucination rate, indicating that they would unable to identify non-relevant passages or say that, none of the passages can answer the question. Secondly, we found that, interestingly, Mixtral and Llama 3.8b, actually, so they are more or less, they suffer less from hallucination, but they have difficulties in observing the relevant passages. So they observe more of over a 40% error rate on the NoMIRACL relevant subset. And third, what we find currently is that like GPT-4o, GPT-4, Llama 370B, and similarly other open large source models provide the best trade-off between the relevant and the non-relevant subsets, at least in NoMIRACL. We also did some prompt optimization, or we did an ablation where we kind of played around with different prompts. So the thing which is mentioned in black was our vanilla prompt. So since we included 10 different passages, our sequence length was really high. So that's why we kind of chose to do listwise, like listwise without any exemplars and the prompt. So our vanilla prompt was 0-shot. We played around by repeating the instruction, providing some roles, or explaining the prompt. In terms of results, what we found was that explanation prompt kind of reduced the hallucination rate on the non-relevant subset on average, whereas the roll and repeat ones kind of reduced the error rate on the relevant subsets. So TLDR was kind of like we found that prompt optimization led to mixed improvements across different models in NoMIRACL.
I have another question.
Yeah.
So like usually when people talk about RAG, people these days also talk about context length of the model. So like models like open source models as well, like with larger context length. So do you think that could also change or make an impact on these metrics? Like in the current setup, I think you fix the prompt to the maximum, I think, right? But what do you think, like if we've had a much larger context, like could these metrics would have changed like for the better or for the worse? Like maybe like using, I think Mistral now does have a larger context model, or Llama also, I don't know Llama has it or not. But like if you have run any recent experiments or anything, what do you think about that?
Yeah, it's a good question. So personally, like at least for MIRACL, so all our passages were broken into like small segments of Wikipedia, which are in general short. And often what I found in retrieval, at least, is that you find a majority of your answers, or the part which is relevant to the question, is present within the top K words. So really, I don't think so. Our data set really evaluates or can evaluate long context evaluation. So I do feel like even if you add longer context, at least the results should remain same for NoMIRACL and also MIRACL. The reason being that right now we truncate each passage to about like something like 380 tokens, so that we have a context input sequence length of 4K tokens. So 380 multiplied by 10 was about 3.8, and we gave about 100, 200 as buffer for the instruction. So I do feel like in our case, even if you extend the context length, kind of the results would be similar. But in general, it really depends upon the like what data set are you evaluating. If you are kind of dealing with law or legal sort of corpuses where your data set is really huge, the PDF documents are huge, and you need to reason across different pages in your PDF document. For example, if you have a 100-page long legal document and you want to refer and reason, I feel like for those scenarios, long context would be definitely useful. But for MIRACL, I don't see adding more context, hopefully, is possibly helping it, because I personally think a majority of the relevant information lies in the first top K 400 words. If that helps.
One last question. So with respect to number of tokens that you fix, is it constant across every language? Because other languages might have a higher token requirement for the same amount of information that, let's say, other languages might not. For example, Hindi or other languages which are morphologically richer languages might require a higher token count to represent the same information where you want to retrieve. So did you face some problem there to handle, like, maybe some trade-offs with error rates or hallucination rate, or like the metrics going up and down because of simply because of the amount of information you cannot feed to the model.
Yeah, that is a good point. So I do find that actually. So I'm not sure how many of these have basically a tokenizer with about 100K vocabulary size, but in general, like for lower resource languages, like we found for Telugu, like the amount of tokens required to represent a sentence was much higher. But it kind of didn't affect our scenario much because somehow the Wikipedia articles in Telugu also were much shorter than what it was in English. So in general, like you would find if you actually check a Wikipedia article, it is very well explained in English. But the same Wikipedia article, if you try to find it in Telugu or some other low resource language, for example, what I've seen is that they are usually less explained. But so I kind of find so right now I choose like a fixed sequence length across all languages. So this can definitely penalize lower resource languages, meaning that I'm incorporating less information from each passage. But yeah, right now for some of these models, I don't remember which ones, but I had an explicit limit that I cannot extend more than 4096. So that's why I ended up choosing 4096 just to be fair across all the different models and their settings. Okay. Yeah, thanks for the questions. Let me move on to the third part of it. So this is the generation part, where I'll be talking about MIRAGE-Bench, which is an automatic multilingual benchmark arena for RAG systems. So this was a recent work which appeared in arXiv, I think, so a few months ago. So like I mentioned, so in part one, part two, we talked about retrieval and relevance. So in part three, we are now focusing on generation, where we are more specifically looking at the RAG answer and how well, we want to evaluate the quality of the generated RAG answer of multiple different, generator systems, basically different multilingual LLMs. We also consider Oracle documents. So these were basically top 10 passages which got annotated in MIRACL. And another important setting in our case was we didn't have any gold truth for the answers. So we don't have any human generated answers in our case. So what I found typically evaluation in RAG benchmarks in two different ways. What I found like there are community which focuses more on traditional or heuristic based. So and also there is community which uses LLM as a judge to sort of evaluate different RAG outputs. So heuristic-based features, in this case, people or the community would handcraft certain different metrics or certain different features and use that for evaluation. So the pros are you are evaluating your RAG systems across multiple different features or dimensions, and it is quick to run these features if you are using more traditional features. Some cons are that comparison is difficult amongst models because you have 10 different features with 10 different numbers across 15 different models. So you really don't know which model is good. So sometimes comparison across models is difficult, and often at times you do require the gold truth to be able to come up with traditional base metrics. On the other hand, when you use LLM as a judge, the pros are you don't really need a gold truth. You do not need to handcraft features. But certain cons are that it can be really expensive to use highly performing LLMs such as GPT-4 or GPT-4o. So it's very expensive to do that. And often there are like issues with biases towards the judge and what kind of a judge you use. So our motivation in the paper was like, why not we try to combine the best of both worlds? So we see that there is traditional and LLM as a judge. Let's try to combine both. So how we actually come up combining both is we try to learn a learning to rank model as a surrogate judge. So what it does is it would actually replace the expensive LLM as a judge. So in our case, we use GPT-4o. And it trains on the computationally cheaper heuristic features, so to give you like a sort of an arena benchmark in the end. So when I look at my pipeline, so first, what I have in the first stage is that I would generate RAG answers for queries and given passages. So with all the baseline models, I would first generate certain RAG answers. Second, I would compute all the different heuristic features. So given the answer, for example, one example is basically citation quality. So I compute citation quality across all the different baselines and similarly for all different heuristic features. Third is I would compute the LLM as a judge score. So this means that given our answer from model A versus model B, basically we use a judge to say which model has a better RAG answer. And combining both the heuristic features, which are actually used to train this learning to rank model, and the labels are actually coming from the Bradley-Terry model logits, where I use LLM as a judge scores. We are able to we are able to train a surrogate judge, which can output basically a leaderboard mentioning which model does well in basically for multilingual RAG. So during inference, what good part is that you kind of can get away not doing LLM as a judge. So the moment you have a trained learning to rank model, you only need to compute the heuristic features and use the model at inference to get or to add newer models to your leaderboard. So it's quicker to run at inference. Certain heuristic features which I chose for RAG evaluation. So we looked into like multiple different aspects which have been followed in the literature, at least both for NLP and also for IR systems. So we look into the language, whether the system outputs in the correct language or not, which is expected. The citation quality, whether it cites the relevant passages. Support or faithfulness, which means that the sentences which are cited, are they really supported by information present in the cited passage? Re-ranker score, which just computes the passages which were cited, and the query re-ranker score. Answer overlap, which kind of computes the answer overlap between the GPT-4 answers versus the system response. So in our case, since we didn't have any gold truth for the answer, we are using GPT-4's answer as kind of for the reference. And lastly, we also compute fluency as a metric. On the other hand, for LLM as a judge feature, so we did evaluate on a pairwise setup with GPT-4o. So the computational cost for this is O of n square if you do exhaustive, because you would compare each pairwise combination of n, where n is your count of models which you are evaluating. So in the prompt, if you see, we ask it to talk about, we ask it to consider different features such as correctness, helpfulness, completeness, accuracy, so on and so forth. And we provide the user question, the reference documents, and both the answers of both the models, and ask the judge to say whether A is better, give your explanation, and then give a final verdict saying that whether A is better, B is better, or C for a tie. So it's more or less something similar to like a chain of thought reasoning prompt. We also tried pointwise and list-wise evaluation internally because I find that both of them are much more efficient than using pairwise setup. But the reason why pointwise didn't work was we found that many of these baselines would actually get an identical score. So for example, like we evaluated about 18 models and 15 of them achieved a score of 4.0. And we found that even listwise was more difficult because listwise involves ranking all of the models in a particular list way, and that was even more difficult for the judge to order. So what we found worked best in our case was the pairwise setup using GPT-4o as a judge. So how we trained or how we designed the surrogate judge was in our case, in the beginning, we actually used random forest for simplicity. And it's also can be easily trained within just minutes using a CPU. We also had to do bootstrapping. The reason is that we had only a few amount of pairs. which we were able to judge using LLM as a judge. So about 50 to 100 queries or query passage pairs, 50 to 50 queries. So this means that almost 5,000 query passage pairs, or it depends upon, sorry, the model pairwise combinations. But yeah, we use bootstrapping to actually generate more training data and also help us better estimate the variance when we are doing the rank prediction. And also we use the Bradley-Terry model, which kind of was originally used in LLMs to assign different scores based on pairwise comparison, where, the Bradley-Terry model, you can have a look at it. So it gives you the log odds of model I beating model J, given in using this probability Pij. Yeah, so if you're interested, you can look through it through our paper. But what we do is we do multiple tournaments. In a way, we, for example, conduct 200 tournaments in which we make all the models fight each other. And with each tournament, we bootstrap a certain set of queries. And using that bootstrapping, we get the final ranks, which are then basically meaned and averaged over the number of tournaments which we play. So some experimental details, like MIRAGE-Bench was actually constructed using the MIRACL dev set itself. So we had queries and Oracle judge documents from the MIRACL data itself, which was a really high quality data, which we invested a lot of time in constructing. So MIRACL evaluated the retrieval part of it. So just to remind that in MIRAGE-Bench we are evaluating the answer part of it. So we break the RAG answer into a reasoning and a answer. So you see there are two places, and this is what we use for evaluation in MIRAGE-Bench. In our case, just to answer the question before, so we did evaluate more recent models because this work was, I think so, just only a few months old. So we do evaluate like GPT 3.5, 4.4.0, Mistral, most variants, 5.3 instruct models, which were, I think so, one of them is multilingual. And also the Command R Plus, IA models, Llama 3, Gamma 1.1, and the Qwen 2 models. So
I have a question in the last, right? So I see like you used, did you use Mistral? It's a base model, right? So the instruction following capability of that model would not maybe probably exist. So
yeah, I think so. I used the instruct model for this one.
Yeah.
I just forgot to add the instruct in front of it. Yeah.
Got it.
Yeah, makes sense. Yeah. Sorry about that. That's a typo on my side. Yeah. Yeah, but just to remind other people, I should have mentioned this, all models are the instruct versions. So I've used all the instruct versions for all models in both for NoMIRACL and as well as MIRAGE-Bench. Yeah, so arena-based results. So this basically shows you the rank of different models which are arranged on average from top to down. So here a lower number means a better rank. So that's why it's coming on top. So overall, a summary for what we find is that, these closed source models like GPT-4 or GPT-4, Llama 3, Mistral, they achieve the topmost ranks in our case. We also found some very interesting observations, like mostly we found rankings to be stable, but some interesting observations were like, 5.3 small, we found performed really well across German, English, Spanish, and Gamma 1.1 performed really well on Telugu, Swahili, and Thai. So if you see in orange, I've kind of highlighted these two parts where they achieve a much more higher rank in general in comparison to other models. So on the right-hand side, I plot the rankings which we get from using the surrogate judge. So I will not go through this in detail, but overall we find that, we get a Kendall-Tau correlation of 0.9 or 9, which is a really high correlation, which kind of shows that, the surrogate judge works well, at least for this case. We had some interesting ablations. So first one was feature importance in the surrogate judge. So in this case, we found that, using the heuristics, actually the answer overlaps were the most important features and also the fluency. So this is very interesting, actually. So, the kind of goes, maybe I can discuss this later, why I think this might be the case. But yeah, in general, the surrogate judge, which is a random forest model, so you can get the feature importance, is actually gives a higher weight to these certain features. We also tried an ablation where we tried different feature combinations. So in our case, what we found works best was if you remove these very low correlation features, actually you get the best surrogate model instead of training for all features. So actually kind of coming up with your handcrafted features and only using those which you think are important works good for training the surrogate judge. Third is we did an exhaustive comparison. So this means that we had 19 models. So we did like 19 C2 combinations for each query. What we wanted to see was like, can we use a lesser amount of queries or can we use lesser amount of pairwise combinations to see whether, how well does this would correlate to the original gold sort of ranking. So in general, both our findings were that, more queries, the better. And also doing an exhaustive pairwise comparison, or more the pairwise comparisons you do, the better you are in estimating the performance or the rank performance of the model. Lastly, we also tried some fine tuning on the MIRAGE-Bench trained dataset. So I tried with 3 different models. I think so. I took the Mistral version 0.2 instruct, 7B1, the Llama 3.8B. So what I found works really well was like the Mistral 7B actually trained or synthetically fine-tuned. So I did SFT on the GPT-4o distilled train data, and it gets the position 2, which kind of does outperform Llama 3 on these 6 languages, which I used for my ablation choice. So this kind of shows that the training data is also useful to improve the smaller models and to get better on the data set itself. So yeah, let's now summarize our findings and briefly talk about future work. So just to recap, basically we talked about 3 parts of the whole multilingual RAG pipeline. Retrieval was the first part, second part where I talked about relevance assessment, and third part went into the generation part. Some highlights and key takeaways. First is data reusability. So we actually constructed a high quality data set in MIRACL and reused it for both NoMIRACL and MIRAGE-Bench. So this is what I found was kind of a crucial point in our whole research. Third is, for retrieval, we found that hybrid search techniques currently dominate on multilingual retrieval, and the commercial APIs we found were not significantly better than the open source alternatives. For relevance assessment, we found that multilingual LLMs, like a broader category, I think so older ones were unable to identify non-relevant passages. So more or less newer and more recent models have better reasoning capabilities. So this is kind of improving, and closed and large open source models performed best. And for the generation part, what we saw is that, you can kind of look into using surrogate judges, which is much more better in terms of cost, and it can be used to approximate LLM as a judge rankings. And also we found that on the benchmark, closed and large open source models, again, they perform the best, and fine tuning can be, useful to actually help improve performances of smaller open sourced LLMs. Conclusions and future work. So what I like to say is that, it's like the whole part was kind of to show you a longer project. So this involved across at least 2 years or something. So, you should invest in longer projects and not just papers. So we reutilize materials. One future work is that since our current scope was only Wikipedia, we want to really extend this to different domains, more realistic ones. But what I've often found is that, finding multilingual data and uniformity, like, for example, if you want news data is available really a lot for certain languages, but it's not available so much for some others. So really finding this uniformity in resources is often challenging. Cross-linguality is the one which we want to really explore after this. So the whole, all three papers kind of delve into the monolingual setting, but ideally we want to extend to different cross-linguality, where, for example, given a creme brulee recipe, which I ask in Bengali, I hopefully would find the best information in some French articles. So ideally, I would want to do like that sort of cross-lingual RAG setup where you have, from like X can be in any language and your Y documents can be in any language. Third is this findings kind of accelerate or help improve LLMs for RAG. So they can be used to help accelerate or improve the multilingual LLMs. I feel like, these works have been a motivation to for existing models. How well do they perform and how can we improve them? And lastly, what I personally would hopefully do is continue investing, because a lot of it needs more effort towards benchmarking, maintaining code and leaderboards, and also continually checking progress. Like once we initially evaluated Llama 3 for NoMIRACL, we found that it was much, much better than Llama 2. So the findings do change with each and every, hopefully, subsequent version of the models which comes. So yeah, so this was overall my talk. Sorry, kind of have only a few minutes for questioning, but yeah, so yeah, thanks a lot for participating. And in case if you have any questions, yeah, feel free to ask. Yes.
Yeah. So Nena has a question. Yeah.
Hey, hi, thanks, Nandan, for a great talk. This was really insightful. So maybe I missed this in your presentation, but did you see big differences between the performances in the different models in all your between performances in different languages in all the three settings that you, evaluated in? So for example, I mean, we do expect that the low resource languages will perform poorly and the higher resource ones will perform well. So I just wanted to ask if that's consistent with what you saw.
Yeah, that is consistent. So what I personally found is that the like gamma models in general, they work well for Indic languages. This is what one of my personal observations. But in general, I've seen consistency in terms of like models performing well across high resource languages, whereas lagging sometimes in low resource languages. But there are some caveats here. So one caveat is that, for example, for a low resource language such as Swahili, the Wikipedia corpus is only 50K documents. So but your English has about like 15 million documents or something. So so really, I sometimes wonder, like, let's say if we have a big enough corpus in Swahili, whether the findings will change or not. But it could be also that, the information present in lower resource languages are like very dense and not really sparse, so because they only talk about a few things.
Yeah.
So maybe this can be one of the reasons why certain models do well. Like, for example, if someone looked at all the Wikipedia corpuses of Swahili, which is just 50K, a model can easily remember what is there in each, versus if someone had to do that for English, because it contains much more information in general. So yeah, I'm not sure about memorization. Might be one thing which we cannot evaluate at this point of time, but I feel like memorization would be a vital one to see really whether, is it because of advanced reasoning or is it because of just memorization on lower resource languages? Yeah.
Thank you.
Yeah, thanks a lot.
Do we have any other questions? We're already short on time. Questions. Cool. All right.